pH. So let's just briefly appreciate that pH is by definition the concentration of H+ ions, given that it is a negative logarithm. The lower the pH value, the more acidic the environmental solution, as compared the higher the pH, the more basic or alkaline it is. 7 being neutral, 0 being most acidic or 0.1, and 14 being the most basic or the most alkaline. Remember again, as we go from 7 down towards 0, the H+ concentration increases, and as we go from 7 up to 14, the hydroxyl ion, i.e. the OH- concentration increases. That's a general overview. Now moving on to actual pH in the human body. So the range is very narrow. It's, depending on different references, generally speaking, 7.35 to 7.45. There are a number of reasons for which the pH in the human body can change, but for the most part of it, this is associated with respiration or metabolism. As far as the respiratory elements are concerned, we're going to look at the partial pressure of carbon dioxide and the partial pressure of oxygen. As far as the metabolic processes are concerned, we are going to look at what we refer to as the base excess and the carbonate ions. So, looking first at carbon dioxide and oxygen, i.e. the respiratory elements, we need to appreciate the fact that carbon dioxide is toxic metabolic waste. It is therefore acidic. If I increase my carbon dioxide levels, then the pH is going to drop. If I decrease my carbon dioxide levels, then my pH is going to go up. So therefore, I will have respiratory acidosis or respiratory alkalosis, respectively. Now, looking at oxygen in equal fashion, oxygen is actually not acidic. On the contrary, it's quite the opposite. We will treat it as though it is basic or alkali. A reduction in oxygen will lead to a reduction in the pH, hence making it more acidic. This is respiratory acidosis. If we have an increase in oxygen, that is respiratory alkalosis, because the pH will have gone up. Now moving on to the metabolic aspects. So the metabolic elements, we'll have a look at base excess and carbonate ions. Now both of these are basic. So the normal range for your base excess is -2 to 2. So -2 to +2. And your normal range for your carbonate ions is from 22.0 to 28.0. Again, give or take depending on the references and as per trust policy. As I said, both of these are basic. They are both alkali. And so therefore, if we increase the concentration of either the base excess or the carbonate ions, it will lead to metabolic alkalosis, because remember we said this is metabolic. This is all controlled by the kidneys. So metabolic alkalosis, because both of these are basic, and if you increase the amount of base product, we're going to become more alkali. The pH is going to go up. If we decrease these guys, then inevitably we have reduced the amount of base in the blood, and therefore making the environment more acidic. The pH is going to drop, and therefore we will see metabolic acidosis. And this is where we get these terms respiratory and metabolic acidosis and alkalosis. Now, to contextualize this, what we generally see is that you may have a patient, for example, who has got metabolic acidosis. So what happens is they've got a reduction in the base excess, and a reduction in the base excess will lead to metabolic acidosis, except the body will try to compensate, and because it wants the pH to be between 7.35 and 7.45. So in the situation that you've got a reduction in your metabolic bases, i.e. base excess and or carbon ions, the pH is going to be less than 7.35. What does the body do? It compensates. And how is it going to compensate? Well, it's going to engage the other system, which is your respiratory system. And so what it's going to do is it's actually going to create an environment where we have got a reduction in the amount of carbon dioxide and an increase in the amount of oxygen. And the reason for that is because, like I said, we had metabolic acidosis because of the reduction in the metabolic base. So going to the respiratory elements, the carbon dioxide is toxic. So if I reduce that toxicity, I'm compensating for this acidity so that it pushes the range back into the norm or towards the alkaline side, i.e. back towards the norm, and again increasing the amount of oxygen because it has a basic quality, it's going to push it back towards the normal range. If we then, on the back of this, acquire a pH that is in excess of 7.45, or rather, let's go again. If we now achieve a range within 7.35 to 7.45, we will call this picture metabolic acidosis with complete respiratory compensation. If we don't quite reach the threshold between 7.35 and 7.45, we will refer to this as metabolic acidosis with respiratory compensation. Because that compensation is not complete, we will not refer to it as complete compensation. In equal fashion, let's go on the other side. So let's say, for example, the base excess is high, it is raised, and so we have metabolic alkalosis. So what's going to happen here? Well, carbon dioxide is going to increase and oxygen is going to decrease. An increase in carbon dioxide will increase the acidity of the environment. Because we are already in excess of 7.45, i.e. in a metabolic alkalosis state, what the body is trying to do is compensate through the respiratory system to acquire more carbon dioxide to make it more acidic and bring it back within that range of 7.35 to 7.45. Again, if it achieves a situation where it falls within that range, within the normal range, this is what we refer to as metabolic alkalosis with complete respiratory compensation. And if it doesn't quite reach that threshold, reach the range, then it's metabolic acidosis with respiratory compensation. The same application is made the other way as well, from respiratory to metabolic. However, what we appreciate is that your metabolic compensatory mechanisms are much slower because they occur in the kidneys, whereas the respiratory compensatory mechanisms are much faster because it is to do with ventilation, movement of the air in and out of the alveoli, and therefore we don't necessarily see the same pictures to the same extent. Point to note here is in the context of, say, for example, a patient who has COPD, we look at something called chronic retainers. Now, chronic retainers in COPD, so patients with COPD, the O2 sats in these guys, as you'll appreciate from the O2 sats video, is actually slightly lower. Now, this isn't true for all of them, and I might have mentioned that on the previous one. This only occurs in patients with chronic retention of carbon dioxide. How am I going to see chronic retention of carbon dioxide? Well, what you'll see is that you'll find a metabolic alkalosis picture. So your base excess and your carbon ions are raised, and the reason they are raised is because that patient holds carbon dioxide, i.e. they have chronic retention of carbon dioxide, thus they have a chronic environment that is acidic, and that must be compensated by the body. Again, the metabolic compensatory mechanisms take much longer to work, and so the kidneys have adapted to that by increasing the amount of bases that they produce, i.e. carbonate and base excess, and therefore that's how we define what we call chronic retention in COPD. So on a blood gas, you will see raised base excess and carbonate levels in the context of a raised CO2 level. Thank you for watching.